The purpose of this video is to go over an example of a first-order linear circuit, one containing either an inductor or a capacitor and one or more resistors. And in this circuit there is a DC source. So here's the example we're going to be looking at. In this particular circuit, it's laid out so that there are two DC sources and three resistors and an inductor. There is a switch in this circuit that moves from position 1, where the switch is touching position 1, up to position 2 at t equals 0. So one of the things that we will say that's true about this circuit is that it's in the steady state at t equals 0, just before the switch moves from position 1 to position 2. And what we'd like to do is to determine what the current flowing through the inductor is for t greater than 0 if the switch is moved from position 1 to position 2 at t equals 0. So when we're at t equals 0, just before the switch moves, we have this layout of the circuit, and you can see that the switch is in position 1. And what this means, though, is that the 12-volt source and the 6 ohm resistor are no longer attached to the rest of the circuit. So for our purposes to do the analysis of this circuit before the switch moves, we can just think of it as not having that piece of the circuit there at all. Now, in this scenario, we say that the circuit is in the steady state, and this means that every current and every voltage in the circuit is constant. And that means that the inductor behaves like a short circuit. So we'll just label it as such. And the current that we want to find is the current for 0 minus, the time 0 minus. And it's the current that would be flowing through that inductor. Now the thing is that in this configuration, any current that flows through the source will flow through the 4 ohm resistor and then will be up at the node at the top and will then have to flow either through the short circuit or the 12 ohm resistor. And we know that because current flows through the path of least resistance, given two alternate paths that are in parallel, it's going to choose the path that has no resistance on it at all. So what that means is it's as if the 12 ohm resistor isn't even there. And so now this is the effective circuit that we have at t equals 0 minus. So in this case, we have a very simple circuit with just one path for the current to flow along. We have the source and we have the resistor. And so applying Ohm's law, we'll be able to get the current. We know that because this current is flowing through an inductor, that it cannot change instantaneously. So this means that once the switch is moved, in that instant when the switch is moved, the current is still going to be the same along that wire. And so we're just going to call it I0. So we solve for I0 using Ohm's law. So it's the voltage divided by the resistance, and we get 6 amps flowing in this loop for t equals 0. And this is what we call the initial condition. We say this is the initial value of the current. We're trying to find what I of t is for t greater than 0. Actually, t greater than or equal to 0. And so this is one of the pieces of information that we need to be able to get a complete expression for the current. So given the fact that we have a circuit that's got one element in it that is time dependent, that is the inductor, and then we have the switch, meaning that there is going to be a change, we know that we can model the current here as having two parts. We can think of the current, the expression for the current for t greater than 0, as having a force part and a natural part. And the force part is going to be due to the sources, or the source in this case, the voltage source. So what we'd like to do is determine what the force part of the current is for t greater than 0. The force part is going to be what the current will be long after the switch moves. And so we can think of that as the current that's flowing through the inductor as t approaches infinity. So what we want to do is take the circuit that we have, the original circuit that's shown here on the left, and figure out how it's going to behave as t approaches infinity. So one thing that's true is at t equals 0, as we know, the switch moves. And when that happens, we then have the circuit where there is now a new stub where there is no connection. We see that the 24 volts source and the 4 ohm resistor, that series combination of those elements is no longer connected to the rest of the circuit. We also want to try to find the current that's still flowing through the inductor as before, and what we'd like to find is I at t equals infinity, which is the forced part of the current. So let's just take out that piece of the circuit that's no longer connected to everything else and look at what we have. So this is the circuit as t approaches infinity. We see that we have a constant voltage source. It's different from before, right, in this part, because now the switch has moved. We have a 6 ohm resistor now and a 12 ohm resistor, and then we still have the inductor. So again, because the source is constant, it means that every current and voltage in this circuit is going to be constant. Every single one will be constant. And so if that is true, which it is, it means that the voltage across the inductor will be 0, the current will be constant, and the inductor will behave like a short circuit. And so now we have another case where the current is flowing through a wire that is effectively a short circuit. And so once again, it means that the resistor that's in parallel to it will not carry any current at all, and so we can evaluate the circuit this way. This is how the circuit will behave long after the switch closes. It will be effectively a very simple circuit with just a 12 volt source and the 6 ohm resistor in series with it. So again, we can say that the current that flows through there is going to be the same as before after this change, and we can just say, okay, this time at infinity is going to be, we can use Ohm's law to get it, and we can say it's 12 volts over 6 ohms, and that's going to give us 2 amps. And so that is the force part of the response. That is the current that will be flowing through the wire, through the inductor as t goes to infinity. So that's the force part, and we want to keep this answer in mind as well when we're trying to get the complete solution. Now, we need to still find the natural part of IT, that's I sub n. And this is the part that's due to the movement action of the switch and is due to the way that the circuit is configured, the elements that we've chosen. And when we analyze the natural part of IT, what we want to do is consider how the circuit will behave without the action of the source. So again, the complete response, the complete circuit, is going to be the force part plus the natural part of the current. We've already found the force part, that is the current as t approaches infinity. So if we look at the circuit, this is the circuit right at t equals 0, and that's what we want to consider, okay, because that's when the switch moves. We're interested in the natural part of I, okay, it's still, again, flowing through the inductor. And again, because it's not connected to the rest of the circuit, we're going to remove that one piece that has the 24 volt source and the 4 ohm resistor in series. And then we're also going to zero the source because we no longer want to consider the action of that source. What we want to look at is the circuit in a source-free manner. This configuration will give us the natural response. This is assuming that there is energy somewhere in the circuit in order for there to be a natural response. And we know that there is, based on what we already saw. We know that when t is equal to 0, the current is 6 amps. So we know that there has to be some energy in this circuit, in the inductor. Now, the form of the natural solution is a constant times a decaying exponential. And the exponent here is minus t over tau. For this particular circuit, this configuration, since it has an inductor in it and some resistors, tau is going to be the inductance divided by the equivalent resistance, and that equivalent resistance is from the point of view of the inductor. So from the point of view of the inductor, there are two resistors in parallel with each other, the 6 ohm resistor and the 12 ohm resistor. So the equivalent resistance is 4 ohms because the 6 and the 12 are in parallel. And that means that tau is the inductance, which is 2 henries divided by 4 ohms, and that gives us 1/2. So now we can express I natural as k times e to the minus t over tau, and that's k times e to the minus 2t. Okay, so now we have the form of the natural response. So once again, I consists of a forced part and a natural part. We can put those two things in. We already found the forced solution. That is the steady state solution at t equals infinity. That's 2 amps. The natural part is k e to the minus 2t. The way that we find k is by applying initial conditions. We solved for I at 0. We found that it was 6 amps. So what we do is evaluate this expression for I of t at t equals 0. And when we do that, we put in 0 as the exponent for the exponential function. And we end up with 2 plus k e to the 0 equals 6. E to the 0 is 1. So that means that k would have to be 4. And this means that I of t, the complete expression, is 2 plus 4 e to the minus 2t. And that is what it is validly for t greater than or equal to 0. Now, if we put in t equals 0, we see that I at 0 is going to be 6, so that works out fine. And if we let t go to infinity, we see that the second term of this expression, the 4e to the minus 2t, is going to go to 0. And so that means that we'll be left with, as t gets larger and larger, then I of t is going to approach 2 amps, which is also what we expect to see. So this is a process that we can use to solve really any circuit of this type. We need to know the initial condition, that is the value of either the current or the voltage, depending on what we're trying to find, at t equals 0. It's advisable, no matter what we're trying to find, if the circuit contains an inductor, that we find the current through the inductor first. So we would find the current at t equals 0. We would find the steady state solution for t approaches infinity, and that will give us the forced response, the forced part of the current. And then to find the natural part of the current, we zero the source, which is what we did here. We took the 12-volt source and turned it into 0 volts, which turned it into a short circuit. And then we evaluate the circuit, knowing that the natural part of the response has this form, k e to the minus t over tau. So putting those two pieces together, we then get the complete expression for I of t.